Hello. Hello, everyone. Okay, so today is the second part of the transformers of lecture 16. And thanks for coming today. Okay, let's start with some announcements. So yeah, thanks for doing the homework 3. And yeah, I know, sorry. So yeah, well, good news is that this is the very last homework. So homework 4 will be out today, this afternoon probably. And we're going to have 2 questions as usual. One is the visual transformer, which we are going to study today. And the second question is metric learning, where actually that's not for phase clustering, but that's still metric learning, but it's not for phase clustering. And the due date is 2 weeks from now. And for this time, no deadline extension will be provided for sure, because we have other things upcoming, which is the final exam and project reports. Final project reports are coming soon. So yeah, I would like to say that with this time, deadline will be December 1st. Okay. Yeah, I know this course is quite intensive. Hope you guys are learning a lot, and this will be help you. Yeah. Anyway, any questions? Okay, no questions. Then okay, Ren.
Professor,
Yes.
Could you please upload the previous paper of the final exam?
Okay. Yeah.
Okay, thank you.
Mm-hmm. Any other questions? Okay. Okay, let's start the second part of the transformer. But before that, we can review first. So let's see. So yeah, I'm going to ask 2 questions today. So let's see. The first one is okay. Anyone who's not turning on their camera? Okay. June, are you here? June? Kim June? Okay. Donguk?
Yes, Professor.
Okay, so in the last class, we learned about noise contrastive estimator, or NCE. So can you explain what it is?
I'm sorry, I think I needed to study again.
Okay, yeah, that was not an easy concept. So yeah, I know it's a little bit hard. Okay, let's ask Jungyu from data science.
Yes, Professor.
Okay, can you briefly explain what is noise contrastive estimator?
Actually, I'm not fully understand the concept.
Okay, you can try. Need to study more?
Yeah, I think so. Sorry.
Okay, that's fine. Let me ask then Dongyu, Jo Dongyu from data science.
Yes.
Yeah, can you explain what is NCE?
I'm sorry, sir. I think I need to study again.
Okay, okay, yeah, this was not easy. I admit that. Anyone who can explain? Volunteer? if you can explain it, I will give you 5 bonus points on your midterm. Okay, Angon? Angon? Yeah, you can start. I can't hear you. Okay, it's on the chat. Sure, okay, go ahead. Okay, it's an advanced way of contrastive learning. Okay, while we are waiting, other students, you guys also think about it or review the material. Okay, so it uses 2 pairs. One is the true pairs, word plus word appeared in the context, usually the same sentence. One is fake pairs, random, okay. And then so we are learning to distinguish true pairs and fake pairs. Okay, that's it. Please type end of sentence if you're done. So eventually classifier should learn the word vector representation EOS. Okay, great. Correct. So yeah, Gon, thanks for studying and volunteering to answer. I'll give you 5 more points for your midterm. Yeah. So NCE was density estimation. Basically, we are going to learn some distribution of the samples. And those samples, we mean the pair of 2 data points. So if those 2 are relevant, somehow, for example, the sentences contain 2 words in the same sentence, they are somehow related. So we would like to learn those distributions from the training examples, which is we call PM. But if we learn that using softmax, then and if the number of vocabularies or the number of possible tokens is too large, then training those softmax is quite costly. So this NCE sets this problem as binary classification instead of the multi-class classification using the softmax. We can just distinguish this if the sample is coming from the actual distribution, which is the PM, or some random fake distributions. So in this way, they actually use the logistic regression to increase the probability of the real samples and reduce the probability of the fake samples. That was what we discussed at the end of the last lecture, lecture 15. So please review that because we're going to see that again, probably today or in the next lecture. Yeah. Okay, and one more question is this. We learned about this model in the last lecture, so I'm going to ask to just explain what it is and how it works using this figure. So let's ask this to 도현, Kim Dohyun. Yeah. What is this model first?
Oh, actually, I couldn't. I couldn't understand the last lecture, so.
Okay,
sorry.
but do you just remember the name of this model?
Last time I couldn't. Yes.
Okay. Yeah. Okay. Then please review the material from the last lecture. Who else? Yeah, this is important. I emphasize that this is really important. 성현, 박성현.
Yes.
Yeah, what is this motor?
It is a transformer.
Okay, and how does it work?
It works like it consists of encoder and decoder part. And encoder consists of positional encoding part and multi-adaptation. And the encoded embedding sequence is also via input of the decoder, and through the decoder, decoder is also consists of the multi-attention tube, and one of them is a masked multi-attention, which acts like remove the afterwards. So it consists of only for the current words and the before words. So yeah, and the embedding words also be a query of the after multi-attention, and the previous encoded embedding word through the encoder via value and key of second multi-attention, and then it go through the fifth word, and then translate the word.
Okay, great. Actually, yeah, Sungyeon explained the entire structure of the transformer quite nicely. So let's just summarize what's happening in this model again. So input is a sequence of tokens, something like words or words in the sentence or some frames in the video or any kind of sequence inputs. And they are embedded initially using some pre-trained model usually. And then we add the positional encoding because in this transformer model, they use only the attentions, which means they don't actually distinguish the position within the sequence because each of those tokens will be the query once, and then once they are queried, then they will compute the similarity to all the other tokens in the sentence using their keys. And then those value embeddings will be weight summed to update the query embedding itself. So actually, they don't have concept of the order within the sequence. So they add this positional encoding using some sinusoidal function. You may remember that. So they go through this multi-head attention to transform their embedding, each token embeddings, to contextualize to other tokens in the same sequence. And then they go to the feed-forward network, which is the token-wise, not the entire, they don't mix the information from token to token here. And then they repeat this multiple times, n times here. And then the final embedding is actually used in the decoder part. And in decoder part, they start with only one token, some special token, indicating the start of the sentence. And then they go through masked multi-head attention, as Sungyeon explained. They mask all the tokens, which is after the current time step, because they should not refer to the actual answer here. And then they go through the multi-head attention, which is cross-motor, not cross-motor, from the encoder. So the query is still from here, the tokens generated so far, and the keys and values are coming from the encoder part. So for example, if we translate French to English, French is the encoder. So je suis étudiant, that means I am a student. Then that we have to have access to that original French sentence to figure out what is the correct English word for each position. So here we actually refer to the input embeddings, and we attend to those to update the token embeddings here. And they also go through the feed-forward network, and these repeat n times again to have the final output. So yeah, that's the transformer architecture. In one sentence, what transformer does is contextualization. Okay, please remember that it's always contextualized to other tokens in the same sequence. And that's why it's called transformer. Its embedding size never changes, and it just updates by contextualizing to other tokens in the sequence. That is the motivation and how it works. And we are going to use these transformer models today for video models and image models and multimodal modelings today and the next lecture. Okay? Okay, so today we are going to start with Pert, which is really famous application of transformer in natural language processing. Even though this course is basically dealing with the computer vision, we have to learn about this because this Pert model inspired a lot of computer vision models. And also we are going to deal with the multimodal cases directly using the text as a token as well. Okay. So BERT stands for bidirectional encoder representations for transformers, BERT. And this is a very large scale pre-training of the word embeddings using some transformer encoder, only the encoder. They don't use the decoder. And this is completely self-supervised, which means this is still the supervised learning, but no human rating is required, which is great because they want to train a model in large scale. And actually labeling the large scale data set is really tedious and time consuming. So yeah, this is a huge benefit of BERT model. So yeah, they only use the bidirectional no masking encoder only. So the overall architecture is very simple. So suppose we have inputs like this. So basically they have two sentences in the input. So yeah, we are going to explain why do they have two sentences. But here, the first sentence is my dog is cute. And the second is he likes playing. So in the very first, they have some special token called class. CLS stands for class, classification token. And in the middle, between the two sentences, they have some separator, some special token called separator. And in the very last one, they also use the separator. So which means you can just think of this as a mark for the at the end of the sentence. So each of these are tokens which will be embedded. And for each of these words, we have 3 embeddings, and these are just directly added. So the first one is the token embedding, which means containing the semantics of that word. So whenever we have this word my in any sentence, we are going to use this embedding. And we are going to update the meaning of this by contextualizing to other words in the sentence. And if we repeat this many, many times with different sentences, then we hope that this model understands when and where we are going to use the word my in the English sentence. Same for all other words. So the biggest difference between human learning or human definition of words versus how computers understand in big neural network-based models like this is human actually defines the meaning of the words, like the dictionary. If we find some words like dog in the dictionary, it explains what is dog in sentences, right? That's the definition of the concept. But in large-scale pre-training models using transformers or some other models in machine learning, just data-driven. So we don't know what the dog is. It is just defined by neighboring words in a big corpus, very huge corpus. So dog is some word that appears frequently with my. So it will probably learn something, some structures that this is something that people want to have, maybe, because it's coming with my. So something like that. So the meaning of the word is just defined as correlation statistics with other words. Not we don't actually directly deal with the dictionary definitions. Okay. So anyway, so embedding will be learned for each word, and some words you may think of that some words have multiple meanings. But in that case, embedding will be learned from both usage depending on the data sets. And then they have segment embeddings. So because we have 2 sentences, we have to mark that which sentence each word is coming from. So EA, embedding A, means that token belongs to the first sentence, and EB means that it belongs to the second sentence. And the separator belongs to the sentence before than that. Okay? And they also have the positional encoding. So from E0 to E10, that's just marking the location of that word in this sentence. So then what they do, so okay, I just explained in Word, but yeah, it's all written here. So CLS did classification token, which we are going to use for classification purpose later. And SEP is the separator token, as I explained. And they have the segment embedding and the position embedding. So please review this later. I just explained everything. So what they do, so they actually try to optimize two tasks, which is the self-supervised. So the first task is masked language modeling. Probably you're familiar with sentence completion questions in standard English exams like TOEFL or TOEIC or GRE or even SAT. So one sentence is given, and what was the task? You need to choose the best pair of these words from the context of this sentence, right? Sometimes it can be just a single word possible, or sometimes it can be multiple, but only one of these usually makes sense. That's how this question works, right? So actually, they just did exactly the same thing for the computers. So because we have really huge corpus, we just choose some two sentences and randomly mask some words like this, blank. And then ask the model to fill it out. And then, okay, yeah, they chose the masking 15% of the tokens randomly, and then they are substituted with some special token called mask. And then we ask the model to classify what would be the correct words for that. So what is the candidate then? For human, we have just 5 options, but for computers, all the possible words are the candidates in the dictionary or in the vocabulary. So it can be like some tens of thousands. So it's, even though it's a tens of thousands, it's a just a single class classification problem. So what would be the best words? And it just outputs the probability of each word based on its estimations using some softmax. So it's just classification problem over the possible words. And we have the right answer in the ground truth. So using that, we can just backpropagate all the loss to the model. And the second task is next sentence prediction. So here's why we need to have 2 sentences. So this is a binary classification problem, and predicting if the 2 sentences in the input are actually consecutive in our corpus or not. So for example, something like this: I'm not going to school today. It is because today is Sunday. So that means those 2 sentences, we can easily understand that those are actually 2 consecutive sentences, which is correlated. But something like, I am a boy, and the earth is huge, which is not connected sentences. Something like sounds like random, right? So because we are dealing with only the sentence level in the first task, we wanted to train some relationship between the sentences in a bigger picture. So this next sentence prediction is doing that. So we just randomly sample 2 sentences in the big corpus. Then probably they will not be correlated. That is the 50% of the data set. And for the other half, we choose the 2 consecutive sentences. So it's just classify whether these 2 sentences are consecutive or correlated or not. So that's the next sentence prediction problem. So again, this MLM is self-supervised. We don't need to label anything. We always have the full sentences, complete sentences, and we can just blank or mask any words we would like to. And we always know the correct answer. So we can just use the collected data set without any human labor. Same thing here. We have very huge corpus, and we can choose any words or any sentences to combine, or we can always choose the two consecutive sentences to create the data set. So both of these are not labor intensive. And according to the authors, their model achieved very high accuracy on this next sentence prediction. And according to their experiment, this was really useful. So they argued that they need both of these tasks to train this model. But later, a lot of people actually tried both, and in a different data set and even larger data set, they realized that this task is much more important than this one. That's easy to imagine, actually. This is much harder task than this one. Okay, so these days, the pre-trained BERT is a default choice for word embeddings. So whenever you're doing any natural language-related projects, consider this as the basis. You can always use this model to extract the meaning or the vector for each of those word tokens, and that will be the actually best choice in many cases. Okay, so we just briefly talked about BERT in natural languages, and now let's talk about the transformer-based image video models. This part is new in this semester. These are really brand new papers, and in last semester when I designed this course, some of these papers were not even published, or it was really new. So I didn't teach this in the last semester. So yeah, if you ask me the Korean lecture recording, this part will not be there. So please concentrate on this lecture today. And you are going to implement this in homework 4. So let's start. VIT, or the vision transformer, is the idea of applying the transformer, something like BERT, into the vision or images, image classification. So yeah, here's the standard transformer model is directly applied to images. So the motivation is this. In natural languages, each word is some good abstraction of some concept. So it's really nice to represent as a vector. And we have quite finite number of possible words in each language. In English, we have, for example, like it is told that we have hundreds of thousands of words. And that is actually the higher side of the other languages. English has more words than other languages. And that's still just hundreds of thousands. So it's not very huge for computers. For us, for human, it's hard to memorize all of those hundreds of thousands of words. But for computers, actually, that's not very large. But for computer vision, when you take an image, even that small size, like 100 by 100, still each of those pixels can have 256 times 256 times 256 possible values in each pixel. And then we have 100 by 100. So it's even in that small image, we have too many possibility of the arrangements of those pixels. So it's really hard to have some abstract representation of some even small image patches. And that's why people was not thinking about this kind of applications for a long time. But now we are kind of seeing that, okay, the transformer is working really well for words. So what would be the counterpart of that basic unit of the concept in the image? So, okay, the basic idea is splitting the image into very small patches, which is 16 by 16, which is very small, even smaller than the icons in your desktop. So each of those small patches may contain only one central topic, and we can learn some concept from that and generalize to the entire set of images. Then that will be performing like the words in the natural languages. That is the main motivation. So an image is split into 16 by 16 patches. Each token is 16 by 16 image patch inside the word, and instead of a word. And the sequence of linear embeddings of these patches are fed into transformer. So each image is split into, for example, 3 by 3. Each of these are 16 by 16 in size. And these 9 image patches are treated like the word in the case of natural language. And we don't know what the meaning of these similar to, we don't know what the dog means in natural language. But whatever it is, we are going to learn some semantics of these tokens using transformer by contextualizing. So image patches are treated on the same way as tokens like words. And eventually, we're going to use this MLP head to classify the input image. So we're going to see how it works. Yeah, it took a lot of time to make these slides. So this is an input image we have. And then we split this image, input image, into 16 by 16 image patches. Or it can be actually, you can change the size. Like some papers use 32 by 32, sometimes 14 by 14. But anyway, some small image patches. So suppose we have these 9s for this input image. And then each of these will become the token, the input token. So let's name that as XP1 to XP9. And these are called input tokens, X. And the size is P by P. So let's say the 16 by 16 or 32 by 32. And then we're going to have one additional special token for the classification, similar to what we've done in Pert. So this will be another token in the same size. And then these will be embedded by a linear projection. Linear projection, what is a linear projection? It's multiplying just some matrix to map this number of dimensions to this number of dimensions. So input is P by P times 3, because we have 3 RGB channels. So the input size is P square C, and the embedding space is D-dimensional. And they used 1024 dimensional vector to represent each token. Compute this, actually. Interestingly, P squared times C is even smaller than 1024. That is an interesting part, actually. They used quite large embedding because they are just multiplying some linear projection. So that will be very weak representation. So these are just very primitive level of representation of these image patches. Then we are going to rely more on the transformer models above this to learn the actual semantics of each of these patches. So these are just starting with quite shady embeddings using this just linear projection. And we had positional encodings in Pert, right? So we do the same thing, positional encoding E pose, which is mapping n plus 1. N is here the number of patches, which is 9. And plus 1 is for this classification token. So 10 numbers are mapped to 1024 because these will be added directly. So the dimensionality of this position encoding should be the same as the input embedding, right? So that's how they decided as the same as this 1024. And then after that, yeah, so these are the formulas directly from the papers. Actually, this is summarizing what we've done so far. So given x1 to xn, which is 9 here, we multiply this embedding linear projection matrix to map it to 1024 dimensional vectors. And we concatenate, not concatenating, we are actually just creating the sequence. Actually, we can concatenate them and add the position embedding, which is also concatenation of all of these 10 position encodings. And then we call it as Z0 because we are starting the transformer layers now. And for each layer, this number will increase. So this is the very basic embedding that have never been gone through the transformer layers yet. Okay, then they go to transformer encoder, which looks like this. Very similar to the general transformer we've learned in the last lecture, except for the order of this. The normalization is coming first instead of the later. So that's the only difference. I don't know why. They just tried this. So here, the first part, it's the multi-head attention. We learned about this in the last lecture. So multi-head self-attention after the layer normalization of Z L minus 1 means we are going to multiply, we are going to have multiple steps of these transformer layers, L times. And this L means its level. So it's starting from 0. L starts from 1, and L minus 1 is 0. So taking this Z0 here, take the layer normalization, go through this multi-head self-attention, and then Z0 is added because of this skip connection, right? And then, based on this, it goes through another layer normalization, then MLP, multi-layer perceptron, fully connected layers. And also we have the skip connection, so this is directly added. And that will be the next level representation, or transformed or contextualized embedding of these tokens. So we repeat this L times to transform each embedding from Z0 to Z1, Z2, and up to ZL. Okay, and then we had recorded we had this classification token at the beginning. So this will be also contextualized with all the other tokens in this image. So this one will have general information about the semantics of this image. And from there, from this embedding at the last level, we stack additional multi-layer perceptron to actually classify what is this image about. So the dataset actually has the label about what is the image, like ImageNet dataset. And we train this transformer to contextualize the token embeddings within that image, some image patches. And then using this classification tokens, we compute the scores predict the scores for each of these classes. So this is it. Actually, this is very similar to the Pert. The only difference is that we are using image patches within the large image, and that works like the word in the Pert. But all others are very similar, just minor details. Okay, so you're going to implement this in your homework. So let's see, how does this work? So VIT outperforms previous SOTA, which was the ResNet, large, really huge ResNet, which is great. And actually, it beats a lot of other great models. But the problem is, here, they took 2,500 TPU version 3 core days. 2,500 days. So if they use 8 TPUs, tensor processing unit, then it takes about a month on this JFT dataset. JFT is a large dataset with 300 million images, but even still, they use Google's infrastructure for months. And how much that will cost? I just computed that. If you are going to use the TPUs on Google Cloud, then you have to pay $8 per hour per one core. So for 1 month, TPU version 3 costs $8. So times 24 hours times 2,500 days, which is $480,000, or in Korean, 5억 won. It's crazy. To train a single model, you pay this amount of money. And actually, when you train a model, you know that we have to train multiple models with different hyperparameters. So each of them actually paying 5억 won all the time, which is crazy. So I'm not going to ask you to do this homework in that scale, but our data set is much smaller, so you can train within a few hours, or at most 1 day. So why do they do this? This is too expensive, even for Google, right? So here's the meaning of this model. VIT performs well only when trained on the very extremely large data set. So this is what they have observed. So there are 3 different data sets. So to the right, the size gets better, larger. ImageNet is 1 million images. And this is ImageNet 21K is the number of classes, not the number of images. And this one is just 1K, but this is 21K, it's like 20 times larger. JFT 300 million is internal data set only available inside Google, not externally available. And they have trained the proposed model on these 3 data sets. And we see that these circles are all the VIP models, and this gray area is the baseline's performance, depending on the size. So on ImageNet, the smallest data set, VIT never outperformed this one, the baseline. This one basically say it's failed on small scale data set. Image of 21K, it was comparable, but still couldn't beat this previous state of the art. VIT outperformed the state of the art only when they were trained on this extremely large data set, which is they pay like $1,000 for each model. So what does that mean? Usually, if we have a good model, that should work well on small scale as well as in the larger scale, right? So let's think about what VIT actually does. VIT does not imply any inductive bias, which is the spatial locality or positional invariance, which we usually assume with CNNs. So in CNNs, each layer has the receptive field nearby each patch's location. So we only learns the patterns observed in the nearby in the image, not the entire image. But in this model, the VIT model transformer, we just put all the tokens as a sequence. And then each of them will be the query. And then they weighted sum the values of all other tokens in the image, always. Right? Just coming back to here. Yeah, they always report to all other tokens in the entire image to learn the relationship between all the pairs, which means they can always report to any other areas in the image from the beginning. So that's why actually they have, when they apply the attention map, even from the beginning, they actually can attend the entire area. So for this dog, they actually attend these areas. So this is different from the CNN. So they have more flexibility. They can always attend other entire image, but that's not always good because it needs to figure out that actually in most cases, the most informational signal is coming from the nearby. That's our common sense, right? So in CNNs, we kind of gave that information to the model that you can just find the necessary information nearby in most cases, but not always. And CNNs actually kind of gave up for those exceptions because we can find the relevant information from the nearby pixels or patches in most cases. But in VIT, they have to learn that fact. In most cases, we can find the relevant information nearby from the data because we didn't give that. We just let them to attend all the possible patches in the image. And they had to figure it out from the data. So that's why they require this large scale data to train on. Otherwise, they lag behind these CNN models because these images are not enough to learn that fact from the data. And then how they can actually outperform these CNN models. Now, trained on this large-scale data for a long time, then they now figure out, okay, in these cases, in most cases, we need to attend only the nearby patches. But in some exceptional cases, we can attend some far away, and then that will be beneficial. So they are also learning those kind of exceptions so they can achieve the better results. So it's not cost effective. They need to pay too much money and too much time and too much efforts to learn that small improvements, but that's actually meaningful scientifically. We can do that. So yeah, so that's the meaning of this VIT work. And the positional embeddings. So as I shown here, the positional encodings are just some embeddings, and they don't do anything like the sinusoidal things. It's just an embedding, and it's learned from the data. And what they did is comparing the similarity between all the pairs. So input patch row in the first and the column patch first, and then that is the most similar to inside this position, and the next, the same row and the same column are less similar, but all others are even less similar. So from this figure, actually, we can see that the positional encoding learns something. So each rows are similar than other rows, and each column is similar than other columns, and the same position is always the most similar. So in short, VIT learns to encode the distance between the images in the similarity of the positional embeddings, and then, yeah, it's just done from the data. So in their discussion, they tried to actually handcraft these two-dimensional in some encodings, because in our previous setting, we didn't have any that information. We just gave from 1 to 9, and they are just learning from the data. But we can actually split them into row ID and column ID somehow like that. But actually, it wasn't that useful. The performance was the same. And the reason is here. We don't have to do that, in short. Actually, they can learn the meaning of each location from the data, and they can actually do this. Okay, so far we talked about images, and now let's move on to videos using the same idea. So naturally extending the idea of VIT to video classification task. So instead of one single image, we have a sequence of images now as input. But all others, the idea is exactly the same. So now each frame is split into n by n. Let's say W and H are the same. So number of the width size and the height size image, and we have the time dimensional number of frames as well. So the total number of patches is multiplying these three. So suppose in the previous example, we had 3 times 3 patches, which is this NW and NH was 3. And this time, suppose we have 8 frames, and we have like 3 and 3, then 8 by 3 by 3 number of patches. So computational overhead is even more serious, because in the image classification VIT model, we pay 400K or 500K per one model. Now we have like 10 or sometimes 50 or 100 frames, then how much we should pay? And what about time? So if we attend all the possible patches within this video, then the time complexity will be like this. If these three are the same, then it's n to the 6. Image VIT was n to the 4, because it has only the two-dimensional rows and columns. But now we have another z-axis, or the time axis. So we have to attend all of those patches, which is not possible. Just, I would say, it's not possible. So what should we do? So just a couple of basic ideas to reduce the computational overhead is not using all the frames. We just sample a few frames to use. So for example, in this one, it samples only 1 per every 2 frames, or you can just choose 1 per every like 15 frames or 30 frames, which means 1 FPS, for example. So for only the chosen frames are tokenized like this, like that. That's one thing you can do. Or extracting non-overlapping spatio-temporal tubes. So this is called tubular embedding. So here, each of these are an image, and the width and height, and this is the time dimension. So if we had only one image, we were tokenizing like this. Just the rows and columns were split like that. But now, in the time dimension, you take a predefined number of frames together. For example, here they use 5 frames at once. So you have the image patches here to here. So this small size p by p times 5 as a small tensor as a token representation. So that is the input to your token embedding. Previously, it was p by p, or 16 by 6, 16 by 16 by 3. Now we have times 5. just that. And that is given as an input, and we multiply the linear layer to map it to some predefined dimensions like 1024, which is the embedding of that tubulet. So somehow like that, we can reduce the number of tokens instead of using all of these small image patches for all frames as a separate tokens. Then it will explode when we do the contextualization. And this brute force model is called model 1. And we're going to propose 3 other models to reduce the computational overhead. The second model is called Factorized Encoder. So the basic idea is, instead of doing the contextualization over all spatial temporal tokens in the video, they do only the spatial transformer first. So each of these is same as image classifier or the VIT. They only attend to other tokens within the same frame, in the same time step. And they only do that within each of those frames. And then each frame will be represented as only a single vector, which is the classification token. We have the classification token at the end of this spatial transformer. Using that as the representation of this frame, very compact representation, and we have multiple of them because we have the time dimensions. We apply the same idea to contextualize to each other to have the final classification in 2 steps. So in this part, the spatial part, the computational overhead for the contextualization is the first part here, an H square and W square. Same as VIT, just image VIT. And then the second part is NT square, because we have the number of tokens here is proportional to NT. Okay? Good. The third model is called factorized self-attention. So previously, we just split the entire contextualization to spatial and temporal in sequence. But now, both of them are given as an input. But inside the transformer block, you apply the first here, the multi-head attention only with the spatial self-attention block. And then followed by the self-attention block for the temporal dimensions. So all of these tokens are given at once. But when you contextualize, in this first multi-head attention, you attend to only the tokens in the same frame, spatially. And then you attend only to the tokens at the same location, but the time varies. Do you follow that? So inside this, you selectively attend, not the entire at the same time. So instead of computing multi-headed self-attention across all pairs of tokens, first only compute self-attention spatially by attending the tokens only in the same time frame to the query. And then in the next multi-head attention, you attend to the tokens at the same location, regardless of the time, to the query. Okay? We're going to visualize how it works in the later slides, which will help you to understand. And the last model is called factorized dot product attention. So remember, in the transformer model, we have multi-headed self-attention. So we have the query key value and small matrices. Remember that in the transformer model, we have actually multiple of them. In the previous model, we had 8 of them in the last lecture. So this idea is split that 8 heads into 4 and 4. And the first 4 for the spatial heads, and the other 4 for the temporal heads. So in this way, key and values are, key S stands for the spatial parts. So these key and values are only for the spatial tokens. So the dimensionality, we don't have the NT here. Half of the attention heads are designed to operate with keys and values from same spatial indices. This part. And the later part is the other half operates on the keys and values from the same temporal indices. So they are called KT and VT. Okay, it's quite complicated, right? They look all the same, but actually they are really different. So if you don't understand or don't follow that, please review this paper. Actually, they explain quite nicely. So this is their experiments. So I explained that the VIT image model is performing really nicely when only if they are trained on very large scale data set, right? Unfortunately, for videos, we don't have that large data set. So what should we do? So what they did was just initializing with pre-trained VIT model on large scale image data set to just compensate for that. And they compared these 4 models, and the best performance was the exhaustive model, which is the slowest. So it was much slower, but it performed slightly better. And the model 2 was the most efficient. But basically, they are not very different. So this is just for your reference. And at the same time, with this Vivid, another model called Timesformer is proposed. As far as I remember, these were from Facebook. So they proposed 5 different architectures. And actually, the first one is the baseline, which is an image classifier, image VIT, the baseline. And this is the exhaustive model, which is Vivid Model 1. And this third one is similar to Vivid Model 3 we just covered. And they introduced these 2. So we can actually understand how they work using this figure better. VIT is delivering only the image. So given this is blue one is the query, then they attend to all the other tokens in the same frame only. They don't deal with other time frames. That's the VIT, just image model. And Vivid Model 1, which is the exhaustive model, and then they attend to all of them, which is the most time consuming. So the main idea of the Vivid Model 3 was attending to the tokens in the same spatial or same time frame, or at the same location spatially. So these 2 at the same position as the query, and these are at the same time frame, but the location is different. They attend to all of these, but not others like this. That's the idea of Vivid version 3. And these 2 are some slight extension of that, like sparse local global attention means this is query, so the local part, which is the yellow, they attend to spatially local and also and temporally local. And the global means they attend to like the stride larger than 1. So they jump in this domain to like attend some far away tokens like that. And axial attention was like this. They attend to at least 1 index should be the same to the query. So the row, column, or time, at least one of them should be the same, then they attend. So not even the tokens in the same time frame with both the row and column are different. So these 9 are excluded. Anyway, so just that they visualize like this, they propose some ideas. Where should we attend, or where we can skip with less loss in the performance. So they just experimented with these, and it's still a very active area of research. Especially this paper was published in this year, and all others are similar actually. So yeah, so we talked about 3 models using the transformers in computer vision, image classification, and the video classification. And we are going to have more papers coming, improving these things. Okay, so this is the end of this lecture. And actually, we have just 15 more minutes. We can quickly the next lecture now. So let me stop the recording now.